force off. So it's going to pick up speed, pick up speed, pick up speed. Although the rate at which it's picking up speed gets less and less, but it's still picking up speed until it hits this point, at which point the force is now pushing it, trying to get it back to equilibrium, so the force is slowing it down, slowing it down, slowing it down, stops it, and then pushes back in the other direction. So it speeds it up, and then slows down, speeds up, slows down. If I plotted it, if going along with what Nick said, the fact that we're dealing with a sine, so position, reverse time, starts out at maximum value, and let's just go ahead and, oh, I already have plus is positive to the right. So the time for one period, that's basically my position graph. Velocity versus time. Period. And then acceleration. Acceleration for time. This is the point when I let go. My velocity is negative, which tells me that when I let go, it's going to start moving in the negative direction, which is fortunate because if I let go and it moved in the positive direction, considering I said positive to the right, we'd be breaking the laws of physics, which actually might be a good thing. If you break the laws of physics, potential Nobel Prize, $1 million coming our way. But let's just assume, just for the moment, that we will not break the laws of physics. The acceleration is negative because the net force is in the negative direction. Matter of fact, the net force is in the negative direction until it hits equilibrium, at which point the net force is in the positive direction, which is this region right here. So we let go, it moves in the negative direction until it stops. This is the turnaround point, and then it starts moving in the positive direction. And it gets back to the starting point. What is my maximum speed?
At the peak of the velocity of the peaks.
Or there.
Yeah. At the
Good. What is, based on the equation, what would the maximum value be? Or do you need numbers?
Yeah, I think I'll need numbers.
You want numbers? All right. So let's make omega equal to 2 radians per second. Let's make like amplitude 3 meters and the mass 4 kilograms. We can figure out K if we need to. But so my position will be 3 meters times the cosine of 2 radians per second. Times time. My velocity will be negative 3 times 2, so negative 6 meters per second. Sine of 2 radians per second times time. And my acceleration will be negative 12 meters per second squared, cosine 2 radians per second times time. What's the maximum speed?
Is it 2 meters per second?
No, it's not 2 meters per second. I assume you're having difficulty seeing, Selena. What is there something you need me to
What's
read to you?
beside the 2? I can't see.
Right here?
Yes.
Radians per second. Just put in the units in.
Gotcha.
It's the
Oh, those are
standard, international standard units for angular frequency and angular speed.
I said meters. I didn't mean meters. I couldn't see the
Oh,
meters.
yeah, that's a rad.
Okay.
All right, so let's think about it this way. I got my graph, I have my equation here, which is describing the velocity. I have some number times the sine of something. What's the largest value sine can be?
One.
What's the smallest value sine can be?
-1.
Yep. So this right here has a range from 1 to -1, or -1 to 1, depends on which way you're going. So at my maximum, what is my velocity? Or let's just stick with speed. At my maximum, what's my speed?
One.
That would just be this piece of it. Don't forget I've got this other piece here.
Oh, it'd be
6 meters per second.
Yeah. This right here is my maximum value for speed. What's my maximum acceleration?
12 meters per second. Squared.
What's my maximum position?
3 meters.
Yep. That amplitude, that number up front tells me my maximum value right there. The other way that we can do the exact same thing is take a look at the energy. There are, at this point in your physics, I think 3 conservative forces. Because you don't do electricity and magnetism in terms of physics. Potentially you have an engineering course that does that, but. Because the physics courses, you got 131, 133. That's it, right?
Yes.
Okay.
Oh, yeah, I wish we did the electricity stuff. Yes. Interesting. We are doing that in our AET class. but
Okay.
It's, we don't learn why electricity does what it does. We just know that it does. That's what.
All right, so conservative forces, gravitational force is conservative. Both kinds, whether we're talking about weight or we're talking about just the generalized formula, such as I'm dealing with outer space, that's still gravitational force. And egoplastic force, which is basically a force that obeys the spring. An ideal spring exerts an elastic force, that negative kx. So 2 or 3, depends on if you want to count gravitational force as 1 or 2 forces. This should cover all the conservative forces we've dealt with so far. Other ones that you might, if you're dealing with some of the electricity and magnetism, the electric force is also conservative. Magnetic force is also conservative. All right, so what do I mean by conservative force?
It's retained throughout the system. It's retained through the system.
What's retained?
The force, the energy, yeah.
Ooh, not, wait, you might have just said it, what?
The energy?
Energy.
Yeah.
A conservative force conserves energy. If it's not a conservative force doing any work here, then energy is not conserved, and so that means it gets passed on to something else. So we can summarize that by the idea that a conservative force, so I'll put a little c there, changes energy from one form to another. A non-conservative force transfers energy from one object to another. Classic non-conservative force, friction. If I slide a book on the table, the book will stop. It loses kinetic energy. That kinetic energy from the book gets transferred into the table. Table will absorb some kinetic energy and become a little bit warmer. So since a spring force, this one we're talking about right here, is conservative, energy is conserved here. What are the two types of energy?
Kinetic and potential.
All right, mechanical energy, I should say. Kinetic plus potential. Seems like we've done some of this 2 weeks ago.
I think you told us not to get into the kinetic or potential energy yet.
Okay. Okay, well, now let's get into some kinetic and potential. Oh, that's right, because we were dealing with the other chapter. So kinetic energy and potential energy, this is potential. Just so you know, in case you haven't been able to tell yet, I use the capital letter U to represent potential energy. And this is kinetic. The formula for kinetic energy is a formula that I do expect you to know cold.
Yes, I do. 1/2 times mass, or 1/2 times mass, times acceleration squared, or velocity squared.
Yeah, speed squared is better. In this case, these are scalars here, so we're actually, it comes down to if you're squaring a vector, what is that exactly does that mean? Typically squaring a vector means you're doing a dot product with itself, which produces a scalar. But in the future, if I ask you what's the formula for kinetic energy, I want all of you in unison to say 1/2 mv squared. Here we go. What's the formula for kinetic energy?
1/2 mv squared.
Not exactly unison, looking for that chorus of angels. We are gonna do it one more time, and I am serious. What's the formula for kinetic energy?
1/2 mv squared.
All right, next time we'll go for enthusiasm, but at least that was in sync. All right. If I ask you what's the formula for potential energy, the proper response is, which one? There's a different potential energy formula for each conservative force. If we are talking about the gravitational force that can be used, where you can use mg, the potential energy formula is mgh, which is probably the one that you dealt with last year, or whenever you took 131. If you're talking the generalized one, the g m1 m2 over r squared, the formula for potential energy is negative big G mass 1 mass 2 over r. Electric force, kq1 q2 over r squared is the magnitude of the electric force, and that would, the potential energy formula is kq1 q2 over r, and I'm not going to worry about the magnetic. Oh, elastic force. Elastic force, the formula, ignoring the sign, is kx. The potential energy formula, 1/2 kx squared. I properly delta x squared, depends on how you want to define things, but it's basically the displacement from 0. So when an object is sitting at its equilibrium spot, its potential energy is 0. I should reword that. Its elastic potential energy is 0. When I have it stretched out to the maximum point, that's when its elastic potential energy is the greatest. I let go, that elastic potential energy gets converted to kinetic energy as it speeds up. When it passes the equilibrium spot, its potential energy is at the minimum, and its kinetic energy is at a maximum. Remember that my maximum speed is a omega, whatever my amplitude is times whatever my angular frequency is. If I looked at this from the point of view of energy, I start out at a maximum energy of 1/2 k times my amplitude squared. That's all potential energy to start with. So my initial potential energy is that, my initial kinetic energy is 0 because it's starting out at rest. And that's got to be equal to my potential plus my kinetic at any other point. So U final plus K final. If I'm passing equilibrium, my potential energy, 0, and the rest of it is all kinetic. 1/2 mv squared. So if I wanted to actually solve for speed, so this is when my potential energy is at its minimum. When I'm solving for speed, I get, well, my 1/2s cancel out. I'm left with Ka squared is equal to mv squared, divided by the mass. I get my speed squared is equal to k over m a squared. I'm gonna square root both sides, so I get v is equal to the square root of k over m times a. And what is the square root of k over m? Square root of k over m? It is.
No.
Still written on the board too. Does that help you? I know there's a lot of writing there, it's extended.
Whatever the little w is.
Omega.
Omega.
Or annual frequency, so that's omega. Okay.
It's in the period equation.
Yes, it is.
I don't remember what it is.
So this is the bit right here that I've written on the board. So from an energy point of view, my maximum speed happens my maximum speed is whatever my annual frequency is times my amplitude, which is exactly what we have right here. Two ways of getting to the exact same place. The beautiful thing about physics, more than one way to look at it. One of the many beautiful things about physics. Anyway, I'm so glad we had this time together, just to sit around and sing a song. But with blanking on the lyrics, let's see. Just sit around and sing a song. And before you know it,
Can't help but sing along.
it's time to say goodbye.
Oh, I thought you were talking about a campfire song.
No, I was doing a Carol Burnett song,
Well,
the way she ended her shows. Carol Burnett, the comedian, had a variety series in the 70s, 60s and 70s, I believe. It is a real treat. Find some video clips of that when you have Harvey Korman and Tim Conway working together, and just see how long it takes before Harvey Korman breaks up in laughter. It was filmed before a live audience. Tim Conway had just that way of making Harvey Korman laugh in almost any skit they're in together. Anyway, have a nice weekend, be safe.
I gotta turn this